Hello, everyone. Thanks for joining in with us today. Welcome to today's topic, systematic approach to testing power swing blocking and out-of-step tripping elements. Here in our webinar platform, you can find that you can move our presentation space around to your liking, as well as discover a few new features, such as learning more about your presenter over here, as well as being able to take our survey and contacting us offline for any questions you'd like to do outside of our webinar. My name is Michael Fleischer, and I'm the America's Marketing and Communications Manager for Megger. I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter team. On the left side of your screen, you will see an Ask a Question window right there. You can submit questions at any time during our presentation, and we will answer them in our Q&A session at the end of the webinar. Additionally, your certificate of attendance, a copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Abel Gonzalez, Senior Applications Engineer. To assist with the question and answer session, we will also have joining us Sugosh Kuber, Senior Relay Applications Engineer, and Michael Wilson, Senior Relay Applications Engineer. With that, I will hand things over to our presenter. Thanks for joining in today, Abel.
Thanks, Mike. Thanks for the introduction. Thanks, guys, for accompanying me in this presentation, and thanks everybody for deciding to use some of your Friday to listen to what we have to say about this topic. Today, we are going to talk about power swing, the fundamentals of power swings in power systems. The difference between stable and unstable power swings, and what's power swing blocking and out-of-step tripping, how power swings are detected, and then the second part of the presentation we are going to devote to showing some methods of testing power swing elements in protective relays. So let's talk about the fundamentals a little bit. Well, when we are talking about power swing, what we are talking is about a phenomenon that happens in networks where because of some faults or because of some increase of load, or sometimes because of some decrease of the load, the generators in the network need to adapt to those conditions, and when the generators try to adapt to those conditions, a condition in the system appears that's called a power swing, because there is an oscillation in the system. When those oscillations are damped and let the system go back into a normal operating condition, albeit in a different operating point, then we call that a stable power swing. And when the system cannot recover from those conditions, then we call that an unstable power swing. Now, for the modeling of these conditions in power systems, for a long time we have used this let's call it 2-source model, where we have a source 1, which we can consider let's say the infinite bus, where all machines are connected, and then on the other side we have the machine where the oscillation is being felt or is being investigated, right? So in any of these models, we can establish the power transfer equation, and the power transfer equation is going to be given by the product of the voltage of the sending source, or the original source, and times the voltage on the receiving source, divided by the total impedance, and the total impedance is going to be the sum of all the impedances that are between the 2 sources. And then this will be multiplied by the sine of the angle between sources 1 and 2, or the sources that we have under investigation. Now, what this equation comes down to is this behavior. Remember that we're talking about a sine here, and the sine is maximum when the angle is 90 degrees. What that tells me is that the maximum power transfer occurs when the angle between the two sources is 90 degrees. You don't want to be in that point, the maximum power transfer, because that is a point that's not very stable. Typically, machines are going to be at a much lower power transfer angle. And in this place here, what happens is that the machine, remember that the machine is, we're talking about a generator. The generator moves because it has a prime mover, which produces a mechanical torque, and that mechanical torque is balanced with the electrical torque that is demanded of the machine because of the loads that are demanded of the machine. So as long as there is a balance between the torque produced by the prime mover, the mechanical torque, and the electromagnetic torque, then the machine is said to be moving at a constant speed. And typically that speed is going to be the synchronous speed of the machine, which will produce the 60 hertz that we are used to. Now, when for some reason the machine either loses some load or is required to transfer more power, then that balance is broken. Let's say that we have, for example, a fault, and because of the fault, one line that was connected to that generator is suddenly lost. What happens is that the machine is suddenly going to lose some of the load that was connected to it. And when the load that was connected to that machine is lost, then the machine starts to accelerate, because now we have a mechanical torque that's going to be greater than the electromagnetic torque that's being demanded of the machine. So when the mechanical torque is greater than the electromagnetic torque, the machine starts to accelerate. And the machine will accelerate until it finds a new point of equilibrium. Now, in that new point of equilibrium, the machine cannot stay there, because it will now have a frequency that's greater than the frequency of the system. So the machine is going to try to go back into the frequency of the system. And as long as these two areas, and this is one of those, let's say, most well-known figures in electrical engineering, and this is called the equal area criterion. And what the equal area criterion says is that as long as the areas under the curve that correspond to the accelerating, remember, when the machine is moving forward, it's moving at a higher speed, it's gaining speed, because the prime mover now has a torque that's greater than the electromagnetic torque that's been demanded. It's accelerating, and as it is accelerating, it is gaining energy, right? And remember that the energy of a body is the kinetic energy in this case is proportional to the square of the angular or linear speed that the body has. So now we are gaining energy, and at some point we're going to have to lose that energy. If the amount of energy that we gain equals the amount of energy that we lost, then we are said to be in a stable power swing, because there was a swing, yes, the machine went and gained some speed, but then it came back and was able to return to a normal stable operating condition. That's normal. That happens very frequently in the system, and it's rarely noticed unless it is a large power swing, which can also be stable, and they can be because of faults that happen in the system, or they can simply be because of the increase or decrease of loads that also happen in the system. Now, when the amount of energy that's gained in one of these processes is greater than the other, then we are talking about an unstable power swing. And in this case, the machines that fall into these conditions cannot return to synchronous speed, and they lose synchronism with the system. So one of the characteristics of the stable power swing is that after the fault, the machine returns to synchronous speed, And one of the characteristics of the unstable power swing is that after the fault, one or more of the machines that are in these conditions are not able to return to synchronous speed. They lose synchronism with the system, and they need to be taken out of operation. Now, there is more to it than that. I'm just going over the basic concepts here that will help me explain the things that I have to talk about later. Now, going back to that same two-source model, we now want to explore what is going to happen with the impedance as seen by a relay located in this point here. So what I want to see is what happens with the impedance seen by a relay, a protection relay that is located in this point here, in this area here. Now, this relay is going to see a voltage, which is the voltage at this bus, and it's going to see a current, that is the current that circulates on this system. So the impedance is going to be the voltage divided by the current. Now, we can say that this voltage, Vs, is this voltage at the generator minus the current multiplied by this impedance here. Okay? And we can say then that the current that we have here is going to be this voltage minus this voltage here divided by the sum of the three impedances. This is what I have in this equation, and the other one is the equation for the voltage that I mentioned before. So when I divide them, I get to this equation where I have the impedance represented as a function of the voltages on both sources and the total impedance of the system and the impedance of the sending end, or this source that I have here represented as source 1. Doing some mathematical, rearrangement and considering the ratio of the sending voltage divided by the receiving voltage here, considering that it's equal to this complex number, then I can say that when the ratio equals 1, I can get to this equation here. And why do I want to get to this equation here? It's because I know that this equation represents a straight line in the impedance diagram. And this would be this straight line right here that's on the impedance diagram. Now, if the ratios are different, if the ratio, for example, is greater than 1, then I have a circle or a group or a family of circles, and if they that move up in this direction, you can see this in some texts. You can see a family of circles, and then that's a very confusing diagram sometimes. And if the ratio of the sending source divided by the receiving end, remember this is ES and this is ER. So it's the voltage on this generator and the voltage on this generator. If this ratio is lower than 1, then I have a group of circles, but they're going to be looking down. Why is this important? Because all of these green lines, which represent that straight line that I was telling you about, or all these circles, they represent the trajectory of the impedance in the impedance plane. When you read the protection text, they'll tell you this is the locus of the impedance in the impedance plane. So you can see that when a power swing is happening, remember that in a power swing, one of the things that happens is that the angle of the machine is moving away. And remember that this angle is simply the angle between these two voltages. So what's happening during a power swing is that even if the voltage remains constant, which is something that could happen if the machine has a voltage control system that can basically maintain the voltage at different speeds by varying the amount of the excitation in the system. If even if the voltages remain constant, since during the power swing the angle between this voltage here and this voltage here is going to change. Now the angle between these voltages is this angle here that I have represented here, and you can see that as this angle changes, then the position of the impedance in the impedance plane is going to change. When we have that particular case of ratio of the voltage on the sending end divided by the voltage on the receiving end equal 1, then we have this straight line. For all other conditions, then we have these arcs. And the importance of this is that this lets us know how the impedance is going to move through the impedance trajectory, or through the impedance plane, how the impedance is going to move in the impedance plane when we have a power swing or a power oscillation in the system. And the importance of that is that an impedance relay placed here, this is the impedance that it's going to see. And see, one of the problems is that the relay initially is going to see that the system is operating away from its characteristic in the load area, for example here. But as the power oscillates, and remember, we are not talking about an actual fault in the system. We're talking about an oscillation that's typically a slow movement of the voltages and the currents. The impedance is going to go, and it can get into the characteristic of the relay, making it trip. Now, if you have a stable power swing, what's going to happen is that the relay will see the impedance going in, but if the power swing is actually stable, remember that if the power swing is stable, the machine will move, the angle will move in this direction, but then the angle will go back and reestablish itself at a value of the angle that's actually closer to the value of the angle of the load, right? So what's going to happen is the angle is going to move there, but then it's going to come back and it's going to get out of the characteristic. It could do it like this. It could do it like that. It could do it in many different ways. It could do one loop. It could do several loops until it gets out. But the point is, it's going to go in and it's going to get out. Now, you do not want your impedance elements to trip during then a stable power swing. You want your impedance elements to avoid tripping during a stable power swing. And for that, what you do is you apply a type of protection element that's called power swing blocking element. It's element 68 in the ANSI protection codes. You call it, it's element 68. It's called it's a blocking relay, but it's also called a power swing blocking relay. Okay, so during these conditions, what you want is you want to activate something that says, okay, this is a power swing. I don't want you guys to overreact and trip and make things worse. Let's let this thing play out, and we'll see if this actually becomes a problem later. Now, an unstable power swing, what happens in an unstable power swing, and remember this graph that we have here, and as we see the trajectory move towards the impedance towards the relay, we see that this angle, the angle between the sources, is going to increase, right? Because we are talking about we are here, then we are here, then we are here. The angle is actually increasing all the time. If the angle starts to go back, then we have a stable characteristic, and we can say, okay, we went there, and then we came back, and we are moving, no problem there. But if the angle keeps increasing, and it gets to this area here, then we can say that it's very hard for this system to recover. Actually, there is a number that's mentioned in the NERC document that says that if the angle between the sources goes beyond 120 degrees, the system is unlikely to recover. And the point is that this is what we use when we are talking about unstable power swings. If the angle goes beyond a certain point, then we declare this an unstable power swing. Now, for an unstable power swing, we do want to declare something called an out-of-step condition. In this case, that condition, when you detect an out-of-step condition, then you want to either trip that generator or you want to trip in a place in the power system where tripping actually makes things better. What I'm trying to say is that you don't always trip in the place in the system where you detected the power swing. You trip in the place in the system where previous power system studies determined that is the best place in the system to bring the system back into a stable condition. Even if you have to break the system into pieces and have islanding in some areas to allow the generators, even some generators may have to just completely get out, and then you have to reconnect them to the system. But the idea is that you have an out-of-step condition. You want to put the system in the most favorable conditions in order to get it back into operation. Now, how are power swings detected? Well, you guys saw that when we have a power swing, the impedance moves into the characteristic of a relay, but it also happens that you saw that the power swing itself doesn't happen instantaneously. It takes a little bit of time for the impedance to move from one place to the other. Let's think about it for a moment. If we had a fault, and we had, for example, this condition of operation here, and there is a fault. When there is a fault, the relay trips. The impedance in the system moves almost immediately to the impedance of the fault. So the movement from this point where the system was operating, the load point, to the fault point happens very quickly when you have a fault. But when you have a power swing, that movement happens ever so slowly, because we are talking about the inertia of large machines, which is one of the reasons why the power swing occurs in the first time, in the first place. So the power swing doesn't allow the impedance to move very quickly across the impedance plane. So one of the things that you can use to detect that there was a power swing is the time that it takes for the impedance to move from one place to the other. You can use the whole impedance, you can use the resistance and the reactance, and do some mathematical comparisons between them. One of the things that is used is something called concentric characteristics. In here I have two concentric mole characteristics. We could have concentric quadrilaterals, for example. It's also very common. It's mentioned in every document out there. And what you do is you decide that you are going to put some separation between these two, and your power system studies will tell you what is the actual time that you can allow for the impedance to travel in this trajectory without having to trip. If it travels too fast, then you may have to declare a trip. If it stays stagnant, then you may have to declare a trip. But as long as it's moving and it's not moving faster than you think it should move, then you're good. If you there are variations of this. You have, for example, the blinder schemes. In this case, I'm talking about a two-blinder blinder scheme. In this case, what we do is we put blinders on both sides of a characteristic, and instead of using a concentric characteristic to start the timing, we use the moment when the characteristic starts. When the impedance crosses this boundary, and the moment when the impedance crosses this other boundary, and we time the difference between these two. We can trip into when we are going into the characteristic. We can trip when we are going out of the characteristic. There is pros and cons for each of those schemes. Another scheme that's not that popular, but it's mentioned by everybody. It's this arc dot. Now, arc dot in this case, what it means is just the derivative of the resistance over time. And what you do is you create a plane in which you have the derivative of the resistance and the resistance itself, and then you create a function that's this line here, which is a function of that resistance and the rate of change of the resistance. And if you are under the characteristic here, then this is the area where you have to operate, and this would be the area where you don't have to operate. Another one that's also mentioned everywhere is the one that's called continuous superimposed current variation. One characteristic of power swings is that the current doesn't increase very much, and it doesn't increase very fast, but it does increase steadily during the increase stage or segment of the current of the power swing. So what you do is you declare that a power swing is happening when the ratio of the two-cycle measurement divided by the previous two-cycle measurement is greater than 5% of the nominal current of the relay. And what you do is you measure this continuously, and what this is doing is that if the current increases too fast or it increases too much, then you declare a power swing and you trip. This is independent of the voltages, so it's a scheme that's used that doesn't depend on voltages, so it's less prone to the errors that we have when we incorporate voltage and current into the same measurement. Now there is the continuous impedance variation, which this one. Okay, so this one, what we do is we rely on the change of the impedance, but we do it by measuring the change in resistance and the change in reactance on consecutive points in the characteristic. So then we have three criteria. We have the criteria of monotony, we have the criteria of continuity and smoothness. Monotony, what that ensures is that the direction of movement has not changed by checking dr and dx. So what happens is that if you're moving in this direction or you're moving in this direction, that's a monotone movement. So it means that you're always moving in the same direction and moving either in or you're moving out. But if you do something like this, and I measure here in this point, and then I measure here in this point, then obviously the resistance is going to have a change from less to more when it should have changed from more to less. So it's no longer a monotone movement. Continuity, the trajectory should not be stationary. It should not stay in a single place longer than it should. So what you do is you create a time threshold, and you say that if it stays in a particular point longer than that threshold, then you declare that the impedance has become stationary in there, and then you may have to consider a tripping for that condition. And then smoothness means that the movement should be uniform without abrupt changes. So what you do is you say that the variation of the resistance over time from one point to the other should not be greater than, and the variation of the reactance from one point to the other should not be greater than. So if it's not smooth, then you're probably in the presence of a fault or a measurement issue, so you may as well declare a trip. And then there is the swing center voltage. Now remember the impedances. Now here we have the impedance of the sending end, that here we have the impedance of the line, and here we have the impedance of the receiving end. We saw that graph a few slides ago when we were talking about the how the impedance moves in the impedance plane. Now what we are doing is we are measuring the voltages. Now this would be the voltage from the sending end. This would be the voltage at this point here in the bus where we are measuring. Remember that the big problem here is that even though this is an interaction between this guy and this guy, our measurement point is rarely directly where we have the two generators. Our measurement point is in wherever we have a bus or wherever we have a substation, right? So this would be the actual voltage that I am measuring. This is the voltage on the other end, and then we have this point which is called the swing center voltage, which is the location where the voltage value is 0, when the angle between the two sources is 180 degrees. Now, that value is going to be maximum when the angle between these two sources is 0. Of course, this is going to be greater when these two are in phase. Sorry, when this and this guy are in phase, so this is going to be twice that. But it's going to be 0 when this guy is over here and this guy is over here looking in this direction. So this guy is going to be 0. Now, what we do is we create an equation that gives us that the position of the center voltage, or the swing center voltage. Now, what happens is that as the voltages oscillate, there's going to be a point where that voltage is going to be 0. That's the swing center voltage. Now, we don't know, we don't have a measurement of that place because we don't know where that place is located, but we can estimate it using some equations. And what's important is that what we are concerned with is the variation of the of that voltage, and we use the variation of that voltage to declare whether there is a power swing or there isn't a power swing. Now, I have intentionally put all these slides in a dark theme because this is the dark arts. So far, what we have talked about is the mathematical foundations of the power swing detection. But when it comes to testing, which is the fun part, the part that we are more into, I guess, the guys who are in the presentation are more interested into testing. So I've put that part in white so that everyone is happier and easier. It's easier for everyone to come into the testing part, right? In the end, that's what most of the guys, I guess, who are in the presentation are interested in. Now, testing is always mentioned in every single of these documents because, yes, we have these very sophisticated algorithms and we have these very sophisticated mathematical methods of detection of power swings, but if we cannot test them properly, then there's no way for us to verify that is going to operate or if it's going to be any help during an actual outage, right? Now, the most common methods of testing power swing are here in this slide. Now, the older and let's say more common method a few years ago used to be using state sequences. Every single document out there recommends that you do not use state sequences to test, but I have seen many people still using state sequences to test power swing. Not that you don't use state sequences to test, no, but that you don't use it to test power swings in particular because of the discrete nature of this method and the fact that power swings don't happen in these discrete steps. They don't happen, the impedance is now 10 and then it becomes 15 and then it becomes 12 and then no, it goes from 10 to 10.5 to 9.8, to then to, so it actually moves smoother, and the angle varies at the same time. So there's a lot to it, and there's also the waveforms themselves. So even though this has been the most common method of testing, it is not very accurate, and there's a lot of algorithms, new algorithms on relays that this kind of testing may not actually pass. I have, for example, set here a simple sequence. This is 6 states. Actually, I set it up with more states, but what's happening is I start outside of the characteristic, and each of these steps is a discrete step. In particular, remember the continuous impedance measurement methods. This one may not pass unless we can make it granular enough, which is something that I'm going to mention later. Now, what you do is you create a sequence of steps. For example, here I start with a small current. I increase the current a little bit, and I change the angle every time. Then I increase the current more, I change the angle, and so on, until I get to, now with this tool, I could have gone to 100 different states, and I could have been very granular. That takes a lot of time, a lot of effort, but it allows me to do that kind of thing. Here I just show the same sequence of states, a little bit extra steps, where I show what the phasors are doing in each of the different steps, and here I show what is the magnitude of the voltages and the magnitude of the currents doing. This would be the currents are increasing, the voltages are decreasing, which is something that you will see later when we present actual waveforms from power swings. This is something that actually happens. So if the current increases and the voltage decreases, what happens is that the impedance is going to start decreasing. If I move the angles properly, I can see that the angles are going to move in the direction that I want them to move, right? Again, this is not very accurate, and it may not pass some algorithms. Again, I see some people doing it out there. I recommend that they move to a more modern form of testing power swing. Now, there's another way, which is using advanced ramps. Now, this is also discouraged in the literature. Specifically because, or especially because, most of the ramping tools that you have out there only allow you to ramp one magnitude at a time. Now, this ramping tool lets you ramp and change everything at the same time. So you can, at the same time, increase the magnitude of the current, increase the phase angle, decrease the magnitude of the voltage, and you can even change the frequency of the voltages, or the frequency of the current, or both at the same time. And you can do that with a very high degree of granularity. So you can go 0.01 degree and 0.01 amp and 0.01 volt every time, and you can create, you basically don't have any limit in the number of steps that you can use with this kind of ramp. And then you can use one ramp to move it up, and then start the next ramp in the same place where you left the ramp before, and then the other ramp to move it out. Now, this gives you a way more control over parameter. Now, this is still state sequencer, in that each of the states, each of the points in the ramp is a particular state. Now, it lasts, so it's a so short duration of each of those states on the ramp that you can say that this is more like a continuous simulation. So you have way more control over parameter. The ride of the impedance is going to be way more, way smoother, and there's no limit on the number of states. But the waveforms that you create here are not like the real power swing waveforms, even though you could, if you get creative and you have enough voltage sources in your unit and enough current sources in your unit, you could basically put them in parallel and create the same thing that I'm going to show you last, which is the superposition of of waveforms, and you can do it with this tool over here. Now, the other, and this would be the method that is recommended everywhere when you're testing power swings. The method that everybody says is the best method. Now, I have a friend who likes to say that perfect is the enemy of good. And what that means is that when you try to be perfect, sometimes you spend so much time trying to do it that you forget that sometimes good enough is good enough, right? So the point is that, yes, ComTrade is better. ComTrade gives you the actual form of the waveform that you know that you are going to see in the real world. It gives you much more confidence that the test cases that you are using and generating are better, but it takes so much time to prepare, because unless you have real cases that you can actually use to test, or that you have a library of cases previously built by somebody that they can give you and that you can use for your power swing element testing, you have to actually simulate the system, and you have to simulate different conditions on the system, and you have to simulate different types of faults on different positions on the system, and then you have to create a database of cases that is going to be good only for one condition of the system, because as the system evolves, as time passes, the loads are going to change, the impedances of the system are going to change, the system itself is going to change a little bit. So whenever you're going to test again, if you're going to do it with this type of method, you are going to be forced to re-simulate the system and to do it all again. Now, again, this is the best way to do it, but it's a laborious process that requires the specialized personnel. Now, here what I'm showing is just the process. You get your ComTrades from wherever you get them, either from an actual fault in the system. Now, for forensic analysis, this is the way to go, because you would get the actual faults as recorded by a digital fault recorder, a relay, or a specialized digital fault recorder in the system, and then you play those faults into the relays, and you see what the relay is seeing, and then you see whether the behavior of the relay actually matches the expected behavior. So it's I would say that at this point it's a very well known process. I'm showing here our tool. You're simply feeding a ComTrade into the tool. You're feeding it into a relay, and then you get from the relay the response, and then you can even get from our tool the times, and you can compare the times from the relay with the times from our tool, right? But this is a process that requires specialized personnel to develop those simulations and test cases. They need to be changed as the network evolves. It's difficult to target points in the characteristic. You can only test the cases that you have available. It's difficult to generalize. The transient limit on the system are different for different types of faults, but you can create a knowledge base over time. You can maybe use it to train an artificial intelligence algorithm, perhaps. So there's, like I said, with everything, there is its pros and cons. Now, using superimposed waveforms, what we do is, let me see if I can show something that I wanted, and let's go back a little bit to the theory again. So remember this, okay, so this is 32, okay. Remember this model, right, where we had this source 1 and source 2, and we can say that this source, the voltage on this source, it's a sinusoidal function, and the voltage on this source is a sinusoidal function, each with their own frequency and phase. So we have frequency 1, phase 1, and then we have frequency 2 and phase 2 for this guy, right? So what we're doing in the superimposed method is exactly that. We are simply generating a simulation where we have this as our source on one end. This would be the receiving end, okay? This is going to be the voltage magnitude on the sending end. This would be the frequency on the sending end, and this would be the phase on the sending end. And in this case, I'm going to have the voltage, frequency, and phase on the receiving end. And I can do this for both the voltages and the currents. So this way, what I'm doing is I am simply using the combined function of the system for both voltages and currents, and when I put them together, I get this waveform right here. If both frequencies are the same, then I wouldn't get this oscillation right here. But since precisely what I'm trying to simulate is a difference in frequencies, because one of the frequencies is going to be the system frequency, that's your infinite bus. On the other side, I have the frequency of the receiving end, let's call it the generator under investigation, the one that's suffering the power swing. So this would be my F2, and when I combine them, then I get these oscillations, and I can change both the voltage and the current, and I can change the voltages and the currents in ways that simulate very well the behavior of a power swing. And then I can add some pre-fault, which is something that's always very important when we're talking about testing with microprocessor relays. We tell the relay, okay, this is the normal condition, and this is where the oscillation is happening. And we can add different cycles to the oscillation, because remember that those oscillations, they are not, they don't go just one time and then they come back. Those oscillations happen, that's why they're called swings. They swing one way and then they swing the other way, and then so they do it several times. And this is not just something in theory, not something theoretical. Actually, in real cases, you can see that those oscillations, they take some time, and there are several cycles of the oscillation, and you want to make sure that your protection is both secure and dependable for those type of operations, right? Now, what we do is we declare the time of the swing, as we saw before, as the inverse of the difference between the frequencies. This would be the time of the swing or the period, and then we can say how many swings we want. This is the actual output from the test set. When you do that, and well, in our and this would be what the phase angle is doing. Remember that the phase angle is very important, and the phase angle is what's going to determine where in the characteristic is the impedance going to be, and the phase angle is also going to tell us whether the system went beyond the stability limit, or if it stays in the stability limit. And then this would be the trajectory of the impedance that we are simulating there. Now, this here is more schematic on this side. So we have a distance protection, we have a single blinder scheme, and this is the power swing that we are simulating. Now, we can get the power swing in here. This is something that only gets in the blinder but doesn't get into the characteristic, but we can also put it inside of the characteristic. We just have to play with these parameters that we have in the model. Now, those parameters, you find them in a tool called Power Swing in our software. That tool lets you decide what's going to be the global frequency, what's going to be the voltage that you want to apply during the power swing, how many what's the period of the power swing. This is the time that I was saying, which is the inverse of the subtraction of the frequencies of the sources on both ends. This would be the pre-fault, And this is the setting time. That's a parameter that comes from the relay, and how many turns do I want. Depending on the number of turns, you'll see that's the number of oscillations that I will see on the waveform. And these are the duration. The duration is calculated depending on the period and the number of turns that I have. And this Z, this is the impedance, the minimum value of impedance during the swing. The maximum value of the impedance is where I start, and the midpoint impedance, which is where I'm going to start, turning and doing my loops. Okay. So after that, I just can run the simulation, and for example, this is a capture that I did here this morning with a relay of the actual waveforms that you see coming out of the test set, and this is how the relay will see it. This is an actual com trait that I captured at 4 kilohertz. I just did a capture of 3 seconds of that that oscillation, and there is also a tool to test. Oh, and this is where you will see the results if there is a trip from the relay or the signal. In the case you're doing power swing, so what you do is you put here the power swing blocking signal, and you verify that power swing blocking signal is asserted for whatever time you think it should be asserted. And then there's the out-of-step testing, because we're talking about power swing. When we're talking about power swing blocking, we're talking about a stable power swing. So we are not talking about a moment when the protection has to trip. We're talking about detecting the power swing and detecting that the power swing is stable. Now, out of step is a condition where we are talking about an unstable power swing. The let's say parameters are the same, except that we no longer have the mid impedance, because this one is going to, remember, traverse the whole characteristic. Okay, so we no longer have the mid impedance, which was the turning point. Remember that we had this characteristic. Okay, let me actually show it a few slides before. So remember that we had this mid impedance, which is where the characteristic starts to turn. In the case of the out of step, what it does is it just goes across. That would be the difference. And this is an actual measurement I did this morning of this same characteristic. This is just a summary of the tool itself. Now we come to one thing that I find which is very important. We have talked about the the fundamentals, the mathematical basis, and we've talked about testing. This is a very interesting, very old, and very active topic. And why do I say all that? Is because you need to read. If you're really interested in this presentation is only like a taste of what you need to know when it comes to power swing and out of step. There is a wealth of information. There is this PSRC report, the Power System Relaying Committee of the IEEE, created in 2005, a report that is called Power Swing and Out-of-Step Considerations on Transmission Lines. This is very good. It's a very thorough source of information. Now, this NERC report, Protection System Response to Power Swings, is a fantastic source of information, because it builds on a lot of the experience that existed before it. Remember that this was created 8 years after the Power Systems Relaying Committee report. And then I recommend also, if you are actually into calculating the parameters for power swing elements and whatnot, I recommend this PRC 026-1 relay performance during stable power swings, which also builds on this report and gets you more into the actual recommendations on how to calculate and how to configure the protection element. Now, if you want to go to the mathematical basis, and I say that kind of laughingly, because I spent a lot of time, you can see it here in my notes, I spent a lot of times trying to, prove to myself that the math that they were showing me in the books and it was actually true. There is this fantastic paper by one of my favorite electrical engineers, Edith Clark. This is from 1945. I forgot to put the date here. This lady, everything she wrote is worth reading it when it comes to electrical engineering. If you are into the math, into the theoretical basis, she has this hand to work equations and things like that. Here she shows the basics the mathematical basis for. And there's also a reference in her paper to another paper that I don't have here. But if you go and read it, you'll see that she talks about a paper from 1930s that talks about these things. Don't think that because that's old, it's obsolete. It's like the Terminator. It's old, but it's never going to be obsolete because that math is going to be there forever. Now, I also recommend this paper from Schweitzer. It's a tutorial on power swing blocking and out-of-step tripping. I took a lot of my, conversational topics from there. It's a fantastic topic. There's also another paper from Schweitzer from 2003, which I forgot to put here. I took one of the pictures that I have. I took it from there, but this one is mentioned. That one is mentioned here. It's also mentioned in these two sources, so I recommend that. And now we have an application note, power swing and out-of-step testing, which is about our tool and how to use our tool. Now, as a summary, well, power swings are very common in the power system. They can be classified in stable and unstable power swings. If you take anything from this conversation, take those three things in there. Power swings, you have to identify them properly to prevent the misoperation of protection elements when the power swing is stable, and to make sure that they operate when the power swing is unstable. That's why you have power swing blocking. You're not blocking the power swing, but you're blocking the operation of protection elements if a stable power swing is detected. And out-of-step tripping, because if the power swing is unstable and the generator goes out of step with the rest of the network, then you have to actually trip. Now, you can test these elements. There's a lot of methods for testing out there. There is state simulation, there's COMTRADE playback, and there is this power swing creation using superimposed waveforms. If you go into the SEL paper that I mentioned, they have a variation on the method of the superimposed waveforms, which I think it's worth reading. And with that, I think we are good, and we can go to questions.
Thanks, Abel. I appreciate you running through this. Before we jump into the Q&A session, a few quick things. For those of you that are leaving, please be sure to fill out our survey there on our bar right there, or in the email following up this email. We really appreciate hearing how we did and how we can continue to improve upon our webinar situation here. So on that survey, there's also a field for you to request a quote or a demo if you are so interested. As a reminder, a copy of the presentation, a certificate of attendance, and a link to the video recording of this webinar will be sent out in about 2 business days. Additionally, the link that you use to join into this webinar now is going to turn into a recording link in about an hour and a half after we conclude here. You can view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar next month called Partial Discharge Fault Location on Power Transformers, which is going to be presented by Saren Gerberts. So let's jump into our questions real quick, and if you have any additional ones, you can enter some in the Ask a Question box there on the left. The first one I have, I'm going to direct over to our panelist, Sugosh. Sugosh, if we have you still on. The question is, which protection elements are affected by a power swing?
Hey, Michael. Thank you for the question. You can hear me, right?
Yes, we can hear you.
When we talk about power swing, be it stable swing, unstable swing, a few functions for sure get affected, like instantaneous phase over current relays. If the line current during the swing, if that current exceeds the pickup setting of the relay, then instantaneous overcurrent relay will operate during the out of step condition, or the unstable power swing condition. um, Even the directional instantaneous overcurrent relays, they'll operate as well if the swing current exceeds the pickup setting of the relay. And also, obviously, the polarizing and operating signals have to have the proper phase relationship during the swing. And then we have the time overcurrent relays. They may operate or may not, but this will depend on the swing current magnitude and the time delay settings of the relay for that particular function. We also have the phase distance relays. They respond to the positive sequence quantities. They also get impacted with the power swing condition. So the positive sequence impedance, which is measured at the line terminal during the unstable power swing condition. So that particular measurement that varies as a function of the phase angle separation between the two system source voltages that we have for the consideration. So, like for example, zone one distance function, which has no intentional time delay, will be probably the first function that would be prone to operate during a power swing. And also, like when we use these distance functions in the relay pilot relaying schemes as well, like you have a blocking or a permissive type of relay systems, even there they could operate. And like backup distance protections, we have the backup zones. They might not operate because since they have some kind of time delay setting, and then that again depends on the time it takes for the swing impedance locus that has to traverse through the relay characteristic. So these are some of the functions that can get impacted during the power swing condition.
Thanks, Ghosh. While I have you, I'm going to direct another question over to you. It's how can breakers be affected by a power swing?
Okay.
So we just took care of protection elements.
Sorry?
Sorry, I was just commenting since we just talked about the protection elements being affected. Let's jump onto the breakers.
Okay. Thank you. So the breakers. So when we think about the out of step trip function in the protection system, the tripping has to be avoided when the angle between the systems is near 180 degrees. So what happens is if a trip occurs during this condition, this definitely imposes like a very high stress on the breaker, and it can cause restrikes and damage the breaker. And there are conditions when you could have like a transient recovery voltage, especially like when you have an out of step condition, right? When you have out of step condition, you call upon a breaker to trip during a system swing, and then this transient recovery voltage is produced. So, and this is extreme when the voltages across the breaker contacts are like 180 degrees out of phase during the interruption process. So if this out of phase is condition like is not addressed, like you could use like a phase angle trip supervision, or if make sure that the breaker is rated for this application. We have to make sure of those things, or else the breaker may fail to interrupt, and then obviously it will result in a breaker failure condition. So this is like a challenge that you would see with the breakers. But then it also depends on what kind of system you have in place, and what is the requirement for us to be able to efficiently manage swing condition using our protection systems, right? So you could have a condition where you need fast fault clearing, especially in certain locations in the system, and maybe your stability studies requires them to be like a fast fault clearing system. So in those cases, you might have to have high speed breakers with high speed relaying systems in place. And then few other applications would be like you might have to have like a independent pole operation of these circuit breakers, just to make your system more efficient the way you would want to design them, It's like, you may want to just, like trip on just a single pole, and then, only on the faulted face basically, and then you have a fast reclose after that. There are a few applications like that where you would have to keep in mind about these things related to the breaker. I hope I answered the question.
And thanks, Ghosh. I appreciate it. Moving on to our next question, I'll throw it over to our presenter, Abel. Abel, of all the test methods presented, which one do you recommend?
Well, like I said, there's the trade-off between availability and accuracy. The ComTrade method is better when you want to be, accurate. When you and when I'm talking about ComTrade method, let's make a parenthesis there. When I say ComTrade method, I say the ComTrades that come from a 100%, or as accurate as possible simulation of the system from something like EMTP or CAPE or ATP or something like that, or from actual DFR recordings, from actual faults that happened in the system. The disadvantage of this last one is that you can only use the faults that happened in this system to test this system, and if you don't have a recording of a previous event happening in this system, then you have to do the simulation. So that would be the most accurate. Now, the more available, the easier to configure, the faster to get results with, would be the one that I called the superimposed waveforms, with which you can also create ComTrades. You're not limited to doing it the way we showed. You can actually get creative with the method. You can do the simulations in Excel and create ComTrades with that, and then play those ComTrades back into the test set, as long as you're able to create a standard format ComTrade, which is not very difficult. It is very likely that there are tools out there that allow you to create ComTrades with 2 or more waveforms. Let's say, advantage of doing it that way is that you can either leave the frequencies constant like we do in our tool, or you can change one of the frequencies, which is something that some people recommend, because that's what actually happens in the generator when the generator is oscillating during a power swing, because the generator frequency on the receiving end does not stay constant during the power swing. The frequency will increase, and then the frequency will drop back down. And if you remember the method that we simulated, it is a good simulation, but it keeps those frequencies constant. If you find a way to actually change that frequency, then that's another way. So I'm not going to say this method is better than the other one. That is up to you, because everybody's conditions are going to be different. Maybe for the engineer or the engineering department, it's better to go with the ComTrade, but maybe for the technician, the maintenance company, the guys who don't have all those resources and time at their disposal, then the other tool is better, and we have a very good solution for that.
Thanks, Abel. While I have you, I'm going to send another question your way. What is the difference between tripping on the way in and tripping on the way out?
Oh, that's something that's also very important. Tripping on the way in means that you trip when the swing or the impedance during the swing gets into the characteristic, and tripping on the way out means that you're tripping when the impedance on the characteristic goes out of the zone, that you are either when you have 2 blinders or when you have 1 blinder. And there are positives and negatives of tripping on the way in and tripping on the way out. Tripping on the way in is faster. It lets you it's a more it lets you prevent issues with the system. But as Sugosh mentioned in his talk about breakers and how breakers can be affected, tripping in the way in can also be worse for the breakers rather than tripping on the way out. So find in the literature, there's a lot of information out there about what's best. And then there are some utilities that are going to say, I'm going to go this way, and some utilities are going to say, I'm going to go the other way. So I guess that's something important. Okay.
Yeah. Thanks, Abel. Next question for you. How will the protection relay differentiate whether to assert element out of step trip or distance trip due to line-to-line or line-to-ground fault? Does it matter if it's first or third zone?
Well, the one good thing about this is that when we're talking about power swing, you never test for, or almost never test for single line-to-ground faults. What you do is, because, okay, let's go back. If you have a single line-to-ground fault or a line-to-line fault, you have to trip for that. Okay? Now, what happens is, what you have to do is you have to simulate different faults in some positions of the system and then see how those faults affect the area where you are interested in the power swing. So my point is, when you are in the line that you are simulating the power swing for is not the line where you are faulted, unless you're talking about a line that you're reclosing into. And then we're talking about a different thing. Typically, when you have a single line to ground or a face-to-face fault, you trip for that, and then you worry, because what happened is when you open the line and you trip for a particular fault, you lost some load, but you also lost the ability to transfer power. So now the new line is going to be either overloaded or underloaded, depending on what the conditions of your system are, and either will create either a deceleration or an acceleration of the rotor, which is going to come down to the oscillations that we are talking about, right? So when I put that stability picture and all the different lines, what I was aiming at was different types of faults will create different scenarios in the system, so you have to worry about those during your simulations.
Thanks, Abel. Next up, can the test superimposed waveform be done only with the STVI or also with the AVTS?
It can be done with the AVTS. I know personally the person who asked that question, former Megger relay applications engineer, very loved by us. I will send him an application note on how it's done.
All right. Then next up, Abel mentioned that during a power swing, the time the impedance changes is slower than a normal impedance fault, normal being parenthesized. How fast does the impedance change during a power swing? Are we talking seconds, milliseconds, etc.?
I also know the person who asked it, also another Megger applications engineer who used to do this thing with us. Hello, man. I hope you're doing well. Well, the thing with power swings is that they're slow. They're slow because there's inertia in the machine, right? Now, when you go into the literature, they say that the typical frequency of power swing is between 4 hertz and 7 hertz. Now, 4 hertz, that's 250 milliseconds. So we're talking about slow for the system, right? Now, in an actual fault, the relay will detect the fault within a cycle or two. So there's a huge difference in time. I mean, not for you and me, right? But for the relay, that's a lifetime, right? I guess that answers your question. And the thing is that what is the actual frequency? That depends on the system that you're talking about. Now, there's a lot of research, for example, right now done about the influence of inverter-based resources into this kind of phenomena. And we don't have answers for that yet, right? But when we have inertia behind the waveforms, then that's what happens.
All right. Thanks, Abel. I think that brings us to the end of our questions for our Q&A session. I'm going to remind everyone that a copy of the presentation we just watched, a certificate of attendance, and a recording of the webinar will be sent out in about 2 business days, if not before. But I'd like to thank everyone for attending. As we conclude here, please remember to answer our survey. We'll be sending out a link to that on our follow-up email as well. That survey will include a field for you to request a quote or a demo if you are interested, and a field to let us know how we did and the topics we should cover. Once again, I'd like to thank you all for attending. I hope you all have a great week. Thank you to our presenter team for joining in, especially Abel for putting on this presentation. And with that, I'll bid you all adieu. Have a great weekend, guys. Bye.
Okay. Thanks, guys. Thank you so much. Have a nice time, man.
Bye-bye.
Thank you.
Bye.
Thanks, guys.